So this is the review for the gas laws test, BCA gas laws test. The test is going to have the ideal gas law, BCA questions, the stoichiometry of how much gas can be produced in a reaction, and IFE charts when we have changing conditions. So I'll do a few of the problems here. I'll start with number 2 here on the front, which is an ideal gas law equation. Remember, our R, our gas constant, is 8.31 and has units of liters, kilopascal, Kelvin, and mole. And those units tell you what all the units in the equation need to be: volume, pressure, temperature, and amount. So number 2 is we have 2.5 grams of xenon. Well, that's our amount, but it's in grams. We're going to have to convert this. It's in a 3-liter container. That's our volume at 80 degrees Celsius temperature, but we know we have to make that Kelvin, and we're asked for pressure. So it's the ideal gas law. There's no initial or final. There's just one pressure, one volume, one temperature, and one amount. Okay, and we're going to solve this for pressure. So we're going to divide V out of the left side. Okay, so we've got N, but we can't use it in grams. We've got to convert first. So we have 2.5 grams. We're going to divide it by the molar mass of xenon tetrafluoride. So it's the weight of 1 xenon and 4 fluorides. That's 207 grams per mole. That means we have 0.0012 moles of xenon F4. So that's our N. R is our constant, 8.31 liters, kilopascal per Kelvin mole, and times temperature, and our temperature is 80 degrees Celsius, but we know we need to add 273 to that, so 353 K is our temperature, and divided by our volume of 3 liters. Now, if we trace the units here, we have moles in the numerator and denominator that cancel, Kelvin numerator, denominator, liters numerator and denominator, and we're left with kilopascals. So if we get out our calculator, it's 0.0012 times 8.31 times 353 divided by 3 gives us an answer of, it's 11.7, and the units are the only units left uncancelled, kilopascals. I'll move to an IFE problem, which I've done a lot of these all the way since last fall, but they're still kind of difficult when there are multiple things going on here. And we'll see how many are involved here. We have a 3.5 liter balloon, so the volume is 3.5 liters in a 72-degree kitchen. Okay, so we have a temperature, but remember, this has to be in Kelvin. So Kelvin is going to be Fahrenheit minus 32 divided by 1.8, and then add the 273 back in. And our Fahrenheit here is 72. So we'll do that. 72 minus 32 divided by 1.8, and add our 273 to make it Kelvin. It's 295. 295 Kelvin. You come up with a brilliant plan to check the gas laws equations you've seen being solved in chemistry class. You stick that balloon in the freezer at negative 15. So we're changing the temperature. It's going to go down. So we've got to solve for K again. So it's going to be negative 15 minus 32 over 1.8 plus 273. negative 15 minus 32 divided by 1.8 is negative 26 Celsius, and you add in the 273, it's 247 Kelvin. This is what will the volume be? Okay, so this is my question mark. And so it's 3.5 liters. We're going to multiply it by this temperature ratio. The temperature went down. That means the particles start to slow down. They don't push against the container as much, and the container's volume should go down. So to make this go down, I'm going to put the big number on the bottom and the small number on top. So the volume is going to go down by the ratio of 247 to 295. So it should go down to 2.9 liters. This right here is 2.9. I'll do one more here. One of the BCA problems. Remember, these things at the heart of them are all about a complete balanced reaction. That's what you need to get every single time. So we'll start with that. This says your car burns 1,000 grams of octane, gasoline, CH18, with excess oxygen. It produces how many moles of carbon dioxide? So the complete balanced reaction is going to be C8H18, and because it's a combustion reaction, it's always got to be mixed with oxygen to produce CO2 and water. Go ahead and balance that. 8 carbons need 8 carbons, 18 hydrogens on both sides. I have 2, 16 and 9 is 25, so we've got an even and an odd. The least common multiplier is 50, so I'll make it 50 on the left. I have 25 on the right, but I need 50, so I'll just double these to make it 50. That makes me double my carbons. Okay, so now I have the complete balanced reaction. I'll do this BCA thing, and I'll do a shortened version of it. It says I have 1,000 grams of octane. Well, I can't do anything with grams, but I can take my 1,000 grams and divide it by the molar mass of C8H18. So it's 8 carbons at 12 apiece and 18 hydrogens, so it's 96 plus 18 is 114 grams per mole. That means I have 8.8 moles of octane. It says I have excess oxygen. I don't really care about water or oxygen though. It's a 2 to 16 ratio, so I will take my 8.8 moles, divide by 2, multiply by 16. It says I should produce 70.4 moles of CO2. And that's the answer. I'm not asking for it to be multiplied by the molar mass of CO2. I'm just looking for how many moles of CO2 can be produced.